Hello guys, welcome back to my channel, Boy. We are still on the process simulation utility series, and today I would like to talk about production allocation utility. This sounds new for some of you. It sounds new for me as well because I found this utility very unique in UniSim design, and I think this is very useful utility, especially if you have a system with multiple feed and you want to track the contribution of each feed to the product stream. So without further ado, I will give a demonstration in two types of system. The first one is system with no chemical reaction, and the second system is with the chemical reaction. Okay, so let's go to the demonstration. Alright, so this is the first demonstration where I want to demonstrate production allocation utility to a non-reactive system. So I have a very simple case here for distillation. As a disclaimer, I don't build this flowsheet based on any PFD heat and mass balance, so I just create a simple and uh, random flowsheet. Yeah, but here what I want to show you is about a system where I have multiple feed. I want to know the contribution of each feed. I want to know the contribution of each feed to the product stream. Okay, so you can use any kind of flow sheet, any kind of simulation that you have, at least that you have several feed and also you have the product stream as well. Okay, so in my case, I'm using a hydrocarbon system from C1 to C6, where I have a varied mass flow and also compositions here. So some have a bigger methane, some have bigger uh, methane and ethane. So the composition is also varied between each feed. Okay, some dominate in the C2, C3. So I want to know the contribution of each feed to the product. Here I already show you the product stream, yeah, with the composition. So what I specify in the distillation is the bottom temperature and also the reflux ratio of 1.2. So I will get a top with -11 temperature, the bottom as what I expect in 51 degrees Celsius. At a glance, at the top, we only have a very few C5. This value can be neglectable, while in the bottom, we have a very low C3. Yeah, so this is how the column separates currently. Okay, so let's try the production allocation utility. Open the utility tab. Then we add the production allocation utility. So here at the first page, we have the available feed streams. UniSim will detect only the feed that is incoming from the boundary, so no intermediate stream detected. But if you want to show the intermediate feed stream, you need to click on this button. But since we don't have any intermediate feed stream, this button don't have the effect in our case. Okay, so I will add all the feed here. Okay, I want to make it in order. Then there is a calculation parameter, run always. So if I tick this, then the production allocation utility will automatically calculate when I already have the feed stream selected. If I tick this, then I select which product stream that I want. For example, the distillate. Then it will show OK. Okay. And if I have an update, for example, I change this into 100,000, then the production allocation utility will automatically calculate the result because I check the run always. Okay. But if I don't, you could see that the selected feed stream have changed. Allocation may need to recalculate. So we need to click the start button to make it running. So that's what it means by run always. Okay. So now we could see the result. So this is how production allocation utility display the result. We have the available product stream. Again, UniSim will detect the most downstream, uh, which is in the battery limit. So if you want to have intermediate product stream, you can click the show intermediate product stream. And there are two product streams in our case, yeah, which is the distillate and also the bottom product. So we see from the distillate first. So what it means with this number is if FIT 5 methane is 25 kilomole per hour, it means that the FIT 5 contributes 25 kilomole per hour of methane to the distillate. Okay, so FIT 4, 4.82 methane contribution to the distillate, and so on and so on. So in short, we could say that the most contribution of methane comes from FIT 5 at the distillate. Okay, if we see the composition of FIT 5, we could notice that FIT 5 have a big methane fraction of 0.3 with a big mass flow compared to the other. Okay, while C4, while it having 5,000 of mass flow, but the methane is very low. So that's why the contribution is not big. Okay, so this is how you track which stream contributes the most for each species. Okay, so if we want to analyze at the bottom stream, so we could see here the most contribution to the heavy phase, which is the N-pentane and I-pentane, is coming from feed 5 and also feed 4. Yeah, because in terms of mass flow, it is quite big. And also, if we see the composition, the C5 is also big. And as a conclusion, we could see that feed 5 have a very big impact to the system because it has a big contribution to the heavy phase of pentane and also the light phase of methane. Besides displaying your allocation in terms of mole, you can also display in terms of percent. Okay. So from here, you could see clearly who have the biggest contributor in terms of percent. If you copy the production allocation utility result to Excel, you could make something like this. We can observe the most significant contribution of the feed to the product, yeah, which in our uh, conditional formatting here, feed 5 and feed 4 have quite dominant result, as well as feed 2 for methane, butane, and also pentane. Okay, if you want to sum, we need to sum it horizontally, yeah, not by vertical, because this is actually not the flow of the feed. Yeah, if we sum this vertically, it will not be summed to 100% because this is not the flow of the feed. Yeah. Feed 5 doesn't mean of 40% is methane, no. But this is the contribution of feed 5 to the product for each species. The next example, I want to demonstrate a system with reaction. Here we have a production of NH3 or ammonia from H2 and N2. Another disclaimer, I don't use the real process operating conditions and also composition because as you see, I use pure hydrogen and also pure N2, which is not right in the real condition. But I only want to show the application of production allocation utility in the case of reaction. Okay, so if we see the result here, I got a 22% of conversion at 200 degrees Celsius. Okay, I want to make the reactor as adiabatic. If we look at the product of ammonia, I have an ammonia with the fraction of 0.12. Okay, so let's move on to the production allocation utility. At utility, then we select all the feed stream. Then I select run always. Okay, so this is the result in terms of molar and in terms of percent. If you're curious on how UniSim design calculate this result, I want to show the calculation in Excel. All right, so in my Excel, I have copied the production allocation utility result and also the mole balance. So I have copied from the stream for NH3 stream, N2 stream, and also H2 stream. Okay, so let's analyze. First, from the unreacted reactant, yeah, we have hydrogen and also nitrogen here. If we could see from the mole balance, this number we get directly from the outlet. Yeah, from here and also from here. Okay, so we can directly get the number from the feed stream. So what does it mean? For H2 in, which is this stream, the contribution of H2 to the product is 9.35, yeah, which is correct because in our product stream, we have 9.35 of H2. The same as well with the nitrogen. The nitrogen flow is 4, but the contribution to the product stream is 3.11. Okay. But how about ammonia? Because ammonia is produced by the reaction. So how UniSim calculate this number? Okay, so we can calculate the amount of N2 and also H2 reacted because the contribution of the feed stream to the ammonia production is by how much the species is reacted in the reaction. Okay, so I want to create a calculation of N2 reacted and also H2 reacted. If we want to calculate N2 reacted, it means we need to minus this by the product. For H2, 12 minus 9.35. From here, we can know how much kilomole per hour of N2 and also H2 reacted. Now, we could see from the reaction balance, N2 plus 3H2 becomes 2NH3. So if we react N2 by 0.88, in order to convert it in terms of NH3, we will divide by 3. So if you want to calculate like the contribution, yeah, N2 contribution to NH3. So we divide this number by 2, okay, kilomole per hour. The same for H2. H2 contribution to NH3. So H2 reacted is 2.64. We divide by 2. Now you could see that our calculation result is aligned with what the UniSim calculate. Here, the contribution of H2 feed to the production of ammonia is 1.32. Yeah, which is the same as we calculate here. And also the contribution of N2 feed stream to the NH3 production is 0.44. And this is also the same as what we calculated. And if we sum these two numbers, it will be the same with the product of NH3 in our product stream. Exactly. Now, if we want to calculate the contribution in terms of percent, we just need to divide by the total. Okay, so this is the H2 contribution. In terms of percent, and also the N2 contribution in terms of percent is this divided by this. Okay, so it will be 75 for H2 and also 25% for NH3. Okay, so this is how UniSim calculate the production allocation utility. Okay, so that's it for the tutorial. We have 2 demonstrations already, the system with no reaction and system with reaction. And I hope you can apply this utility to your engineering study. Okay, so see you in the next episode. Bye-bye.